Great. So I'm really happy and honored to be here. Sydney is beautiful. Thank you, the organizers, for the invitation, and also congratulations on organizing a great conference, a thriving community, and a very nice research program. So what I chose to talk to you today about is some reflections and some of the latest work we've been doing in my lab today. Half of the talk has just been accepted less than 24 hours ago. So I'll really be talking about the latest things and some of the latest papers. And the way I've decided to structure this is really kind of to think about, how do we think of the web and what has the web become, right? And initially, the way we thought of the web was this repository, this library of essentially static web pages. Right, and if you think what that led to is something amazingly remarkable. Right, today the web is large, dynamic, complex. It truly grew far beyond this image of the library that we had in mind. Right. What do we have with the web today is we have documents, we have databases, we have knowledge graphs like DBpedia and Wikipedia, we have IoT streams, we have all these social interactions, social media posts, so it's really kind of the pulse of humanity. It's probably the most interesting, the largest, and the most exciting, the most dynamic, the most complex data set and information artifact we as humanity have ever created, right? And without the web, there wouldn't be the current AI revolution, right? It's actually all the documents that the community, the society created that is actually powering a lot of this, right? So, but the problem is that this heterogeneity and the scale represent huge challenges about how do we deal with this type of information and how do we make sense of it all, right? It's far more complex than this idea of a library. And if you think about, OK, what kind of tools are we using today to navigate this complex information space, I would say we are a bit stuck in the past. Right? Really, we went, I would say, through 2 generations of, let's say, information systems that help us understand the web. Right? The first try, this was a very long time ago when Yahoo was founded and things like that. The idea was we are just going to humanly curate a taxonomy of all the web pages on the web, and then if you will want to find something, you will navigate through taxonomy and find it. Right? That was the initial approach. And then, right about, I don't know, 20, 25 years ago, the next kind of generation of the approach came. And that was, search engines. The realization there was that the web is too big to manually categorize. And the key innovation was that the web is not just a set of isolated documents, but that there is this hyperlink, this graph structure on top of it that allows us to better understand the connectivity, the ranking, the information content of those web pages. But we've been basically with this, almost like stuck with this paradigm of keyword-based web search for a very, very long time. So what I wanted to ask in this talk is to ask, OK, how could we build better, more informed tools that would allow us to navigate the web better and would go beyond the kind of single keyword search or document retrieval, right? To really think about how could we build systems that genuinely understand complex problem solving. And I think today, or this time, is the right time to ask these questions because of the emergence of large language models and the amazing capabilities they have, right? And really think about how do we turn these things that essentially are trained to predict the next word into reasoning engines for these complex information ecosystems. So, and when we do this, we need to be quite careful, right? Because just simply applying LLMs to this complex information landscape isn't simple, right? There is problems with hallucinations, problems with basically grounding the answers in the facts. And this happens as quickly as you go and start asking more precise questions. Problem with synthesizing information that is spread around, perhaps in multiple documents or in multiple data modalities. And also thinking about how do we just go from question-answer type of interaction to much more multi-step collaborative problem solving. So these are kind of the key issues I think, are out there today to really realize the potential. So the plan for this talk that I want to talk to you today about is, how do we augment, let's say, large language models, or how do we build AI systems that allow us that go beyond, just document text retrieval and really think about this as powerful reasoning engines. And there'll be three themes in my talk today. So the first theme will be about bridging structured and unstructured data to be able to answer complex natural language queries. Then I'll be talking about how do we make LLMs more collaborative and why today they are fundamentally limited in collaborative problem solving. And then the last part, I'll show some of the most recent work about automated discovery. Right? So how do we solve the hardest questions, queries of them all, which are scientific hypotheses? So this is the plan. This is the plan for the talk. So first, let's talk about complex information-seeking behavior. And here I have a few examples of, let's say, simple real-world queries that different people might ask in different situations, right? You could imagine an e-commerce-like application where you say, can you find me push-along tricycles from, Radio Flyer that are both fun and safe for my kids, okay? Or, I want to find research papers on social network navigation authored by the researchers from Cornell University, for example. Or, I want to find diseases without known treatments, that induce itching in pregnant women, right? Can I get this kind of information task satisfied? And there's nothing too special about these queries, but if you go under the hood and start thinking, okay, what do I need to be able to answer these queries? They are interesting because they're open textual queries, but they also require some very precise matching, right? Saying, I want a specific brand, I want a specific color, and I also want it to be safe for my kids, right? And nowhere in the product description it will say, this is fun and safe for kids. But maybe this is written somewhere in some review or in some Q&A somewhere deep down on, let's say, the product web page, right? So to really accurately answer these types of questions, you really need to be able to reason over structured information, so basically the structured product database, as well as over the unstructured documents, reviews, questions, answers, product descriptions, and so on. So this is, for example, for the e-commerce case. And the same is actually true for the other two use cases, right? If I think about research papers, it's very similar, right? I only want the ones with the authors from Cornell University. So I really want to match on that property. But then, social network navigation was an interesting research area connected to the Milgram's experiment and the 6 degrees of separation and so on, like super cool stuff. There, maybe I want more semantic type of understanding and matching, and I would like to get research papers, not blog posts, not any other type of document, right? And similar, I gave you this medical Q&A example, the same case here, right? When I ask a question, I want to go back to the medical literature as well as understand the structured information we know about medicine and biology to be really able to accurately, in a non-hallucinated way, answer this question. I'm not sure what happened. Did I press something? Okay. Sorry. Okay. Shall I go tuck, 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 or wait? Okay, we were here. Okay, so what I was doing is I was trying to motivate this idea of being able to search over structured and unstructured information to really accurately, in kind of a non-hallucinated way, be able to answer these questions. Right? And this is hard, right? Because you need to understand both the structured part of information as well as kind of nuanced textual information. Queries, the kind of real-world queries require multi-hop reasoning, filtering, aggregation, and so on. You know, and they require you to kind of reason across these two modalities together. You cannot separate them out and say, okay, I'll do some text retrieval, I'll do some knowledge graph retrieval, and then, you know, everything will work out. And also, what turns out is to be very complicated is, you know, how do I actually evaluate this? How do I measure success? So when we started this research, we first realized there is no good benchmark. Right? If you want to do this kind of complex question answering that requires a bit of reasoning across this, let's say, structured and unstructured data, there is simply no good benchmark. So we went on the path together with our collaborators from Amazon to define this benchmark, and we call it STARK. So it's a large-scale, semi-structured question answering retrieval benchmark that spans both textual and relational data. It covers the three different domains: product search, academic paper search, as well as kind of medical question answering. And it provides realistic complex queries. The way we defined these queries was both have a very small golden set of queries defined by humans, as well as about 10,000 queries per domain actually synthetically generated by LLMs, and I'll explain how we go about that. We rigorously validated these questions, and for every question, we also have the set of answers, the set of target answers and answer entities, so we have the correct ground truth, so we can actually measure success. And the way we basically go about generating these questions is that we would first go into the knowledge graph, traverse the path, and see what candidate entities satisfy basically the relational reasoning part of the query. After we would have that, we would go into the textual information part of the database and ask an LLM to kind of put themselves in the right role and extract some other interesting tidbits from the textual information that the user might be interested in. Now that we have the relational part and kind of the textual part, we go back, filter out the candidates to make sure that the ground truth answers, the target entities, are actually the ones who match both the relational reasoning part as well as the textual reasoning part. And what we end up with this procedure is a large-scale benchmark that spans the three domains I was saying, so e-commerce, academic search, and biomedical question answering. We have about 10,000 questions per each of these domains. We have about, between, let's say, 3 and 17, on average, different target entities that correspond to the answer. So every answer might have multiple results that satisfy it. We also augmented this with about 250, 270 different human-generated questions. And what is interesting is that these questions both kind of span the textual information as well as the relational information. Just to give you some examples of what these questions look like, it could be like, give me sweatshirts for proud Montreal Canadians, right? Or suggest me some Sunto bike, give me suggestions for Sunto bike mounts, or show me papers by a particular author that discuss a particular scientific field, or and so on and so forth. And we have these questions of 3 different types. We have very short type of questions all the way down to much bigger and much more complex questions, right? So as we build this, then the question is, is this a good benchmark? Is it simple? Can today's technology, is it able to solve it? So we actually implemented several different approaches coming from very different backgrounds, but here I'll just show two of them. One is kind of methods that deal with knowledge graph plus text, reasoning, and extraction. We also did a lot of kind of vector similarity search, retrieval augmented generation with a vector database, a bunch of kind of BM25 type retrieval tools, and so on and so forth. And basically what we found is that this benchmark seems to be very challenging for today's technology. So even, here this QAGNN is actually our own work from a few years back that tries to put together structured and unstructured information. It actually doesn't work really well for this type of realistic queries. And also actually this kind of let's textify everything and let's retrieve using vector similarity search and embeddings actually doesn't work really well. So really, what I want to say is that this is a challenge today, right? Is that Stark poses a challenge for these retrieval systems to do complex question answering or to help us answer questions on complex knowledge bases. So the benchmark established the challenge. It's also at the same time a tool to measure progress in this area. And the current approaches need significant improvement to be able to do well on this realistic benchmark. So then, of course, we said, OK, now we have a challenge. Can we go and solve it? So how could we augment LLMs to be able to better solve this type of problems? And our insight was to say, look, this is really about using tools, right? Rather than thinking about, oh, let's just retrieve documents and let LLM reason kind of over them, we really want to allow LLM to come up with kind of the execution plan, use the tools, and be able to find the answer. And when I say the tools, what are these tools? Some of these tools deal with retrieving textual information. Other tools deal with summarizing the textual information, extracting different aspects, keywords, and so on, entities, and then also querying the knowledge graph to get the information from the knowledge graph. Right? So the idea is now with having access to these databases and the ways to query these databases, can the LLM orchestrate it all to give you the correct answer? But what we quickly find out is that actually LLMs are very sloppy when you ask them to do this type of things. They will ignore colors, they will ignore brands, they will come up with very kind of sloppy, this kind of React tool use type approaches that actually don't really work and don't give accurate answers. So then, right, once you are given this and you are like, OK, it doesn't really work, what do? You go and you start prompt engineering and trying to hack it together and spend a lot of time just trying it out over and over again until you get a good result. And we didn't want to do that. We didn't want to go and actually start manually prompt engineering and tuning those things and hoping we get a good result. So what I'll show you is actually a system that goes from an LLM who does not know how to use tools, who gives bad results, to actually a system that knows how to use these tools, that is calling these tools correctly, that is retrieving the information correctly, reasoning over it well, and actually find you let's say, the products, the entities that answer those questions that I was showing earlier. So how do we do this? What are some interesting ideas here? So our insight was that we need to be much more effective in using and telling the LLM how to use these different tools that it has access to be able to retrieve information, reason over it, and find the answer. And if you would want to say, OK, let's do some kind of let's learn how to optimize prompts, the problem is that you cannot do gradient descent over the prompts. You cannot take the derivative with respect to the prompt and say, OK, I'll go and change it. right? So actually what we did is we invented this new technique about how kind of a team of a couple of agents or a couple of LLMs can basically reason about their mistakes, come up with hypotheses about or what those mistakes have in common, and then give suggestions to the other LLM about how to rephrase the prompts. And this way, basically, the system can self-improve as it is seeing more and more queries. And it's able to basically self-improve over time. And this idea behind what we call contrastive reasoning is very simple, right? If you have a student, let's say you are teaching the math, and they do well on some questions and they do terribly on other questions, you don't just tell them, oh, here you did well and here you did a mistake and here's another mistake and another mistake and another mistake. What do you try to do is you try to summarize and kind of contrast where the student is doing well, where the student is doing poorly, and then convey that feedback, right? So maybe based on this, I would say, maybe the student should practice multiplication. That's what's the problem here. So we try to use this analogy, this kind of reasoning, put it into our framework so that prompts can be optimized based on the correctly answered queries as well as based on the incorrectly answered queries. So basically, we define this LLM, we call it comparator engine, that gives insightful instructions to kind of understand the gap between the positive examples, the examples that the current agent is solving well, versus the one when it's making mistakes. So the input here is the actions done by the actor agents, as well as some labeled examples where we know the ground truth, so that we give the LLM the examples of correctly answered questions and the ones where it fails. And basically, we ask it to come up with a hypothesis, come up with some idea how to change the prompt, what needs to improve in order to be able to answer these questions correctly. So we would basically prompt the LLM and say, hey, here are two groups of queries that an agent is performing poorly and well on. Please understand the differences and give us some ideas how to update the prompts. And based on these concrete examples, then the agent actually gives ideas and says, oh, I suggest you better parse and utilize query attributes, do more accurate brand matching, use F1 score string matching to achieve this, right? And based on this, now the LLM can go, the second actor agent can go integrate this into its prompt, integrate this into its tools to do better next time. So we basically now have this closed self-improving loop that allows us to basically automatically invent new tools, allows us to automatically improve the prompts, and this way the system can really, truly learn to do better as it sees its own mistakes. And to give you a sense of what these tools are that we gave access to the agent, it's about parsing the question, parsing the query, extracting keywords and things like that. Those are the tools to access the knowledge graph, traverse the knowledge graph across different relations and so on. All kinds of ranking and similarity, textual similarity, semantic similarity type functions, as well as functions where you can kind of use LLM as a judge or as a summarizer of the results. And basically, now this closed loop system is learning how to use these tools in a better way to answer those queries correctly. And when we run and we basically took our initial agent, which is labeled here in the second line as the React agent, and then we let it self-optimize, we were able to see actually quite strong gains in terms of accuracy. This is hits at one metric of answering these questions. So you basically see that even like this kind of discrete agentic type systems can self-improve and can gain quite a lot of benefit over what we humans are able to engineer. What is interesting is we see this across the Stark benchmark, and we see the same over other benchmarks as well. So here I'm using standard benchmarks like Hotpot QA, Archive QA, and Tool QA. And again, you see how basically we are able to take a base system, and through this idea of contrastive reasoning and refinement of the instructions to the agent, we are able to get quite sizable increases, improvements in the accuracy of answering these questions, and basically allowing the agent to use the tools much more effectively. Right, so the technique I presented is much more general because it can be used in any way where you are basically using an LLM agent, trying to teach them how to use specialized tools to complete the task. And kind of the key idea behind this work is this notion of kind of contrastive reasoning, looking at successes, looking at mistakes, summarizing those, and using those learnings to iteratively improve. This is what I wanted to show kind of as a second vignette in today's talk, right? About basically how to help LLMs better tackle complex Q&A tasks, and rather than we as kind of humans engineering this to death, really let the system self-improve. And it's nice because it's a principled kind of automated way to optimize LLM agents for tool use, right? As we are going to see later, LLMs today are great at using kind of tools that are well documented and have humongous amount of information about them on the web because they are then trained over that data. But as soon as you try to make them use private tools, things get much more tricky. So the second question right now that kind of we can answer these single queries is really, can we go that is the insight that complex tasks don't just involve, I asking a question and me getting an answer, but really it also involves interaction and kind of, it requires evolving goals and it requires going far beyond this kind of single step, one shot, asking a questions, giving an answer. And if you play with LLMs and use them for your daily lives, then I'm sure it happened to you as it happens to me every time. When I ask it something, it immediately comes back with an answer. Then I realize the answer is not what I want because maybe, I forgot to tell the LLM that, I have a vegetarian guest who's coming and, I cannot cook them chicken pasta. Or, I ask them, I don't know, for some advice, and it's starting to tell me about allergies, even though I don't have allergies and things like that, right? So basically, LLMs, the way they are done today, they're very much done in a sense of you ask a question and, ChatGPT will come super confidently back with the answer, kind of jump to conclusions and say, here's what you need, right? So we were really interested in about, how do we the problem is that LLMs are kind of these passive responders, especially when faced with ambiguity. They just assume, right? And they know kind of naturally help users clarify the needs or explore options, right? Maybe another good examples of this is when you walk to a restaurant, right? You don't walk into a restaurant and say, I'm hungry, and then somebody throws a dish in front of you, right? They ask you, how do you feel? What do you like? What kind of taste, food preferences do you have? I don't know, what's your budget? Whatever, right? So they ask you clarifying questions. So the question is, can we build LLMs that will act more as active collaborators and kind of help, let's say, users navigate, complex questions and help them achieve their goals, especially when even the user themselves isn't even sure or hasn't even thought through about all the corner cases and all the possibilities of what their request entails. And there is a kind of fundamental problem why LLMs by themselves are not able to do this today. And the reason for this is the following. First is that we train them on basically the next token prediction, right? So they get reward by correctly generating the next token. Not the next token, not the 3 tokens ahead, but kind of the next one, right? So that's the first one. Then after we've done this kind of base LLM training, we usually go to this preference-based tuning approaches like DPO or RLHF, right? And how this is done, it's done based on human preferences. So basically they show humans 2 responses from the LLM, and the human says, oh, I prefer this one over that one. And then, the LLM is further tuned to kind of give responses that humans prefer over responses that humans don't prefer. But even this is actually a single step. It's a single turn. It's trained on kind of pairwise preferences, on single turn pairwise preferences, right? So these single-turn rewards do not encourage the models to generate solutions that may not be that may be useful in the long term. It just asks, again, it's just seeking immediate reward. So we were actually interested in how do we build, or how could we build, how do we train LLMs to be, to kind of actively seek information from users, kind of as collaborators, and help them kind of effectively navigate the tasks they want to solve. And we tried by basically prompting the LLM and say, hey, ask clarification questions and things like that, and it doesn't really work. So this kind of trivial solution, just tell it to ask questions, doesn't really work. You have to train the LLM to be able to do that. And what I'm showing you next is basically our approach to do this, where basically the key is how do you define the reward so that the reward is really long-term, and to kind of encourage the LLM to be rewarded by the long-term outcome of the conversation, not about correctly generating kind of the immediate next step. So this, what the innovative thing here will be, defining this multi-term aware reward. Okay? So the key question here is, how do we estimate a response to, let's say, a long-term kind of question answering, right? We keep talking, and at the end, I tell you, oh, I achieved my goal, or I did not. And then how do we propagate this reward through all the steps of our conversation, so that kind of when we are, and then we can now train the LLM on these traces to be able to do this. And the point is, right, is like if I have let's say, an open-ended request to an LLM, which could be like, I need to write about how optimism can improve our well-being. The LLM today would just say, here it is, boom, you have it, right? But the other response could be, to get us started, tell me about what tone you are looking for, who the audience is going to be, what is the length of this text that you'd like me to generate, and so on. And then the question is, right, which is better, and how do we quantify this notion of the long-term reward, that maybe in the end the user will be happier to answer a couple of questions and then get the answer they like, versus getting the answer saying, oh no, this is for for I don't know, 10-year-old kids, and then you get something else, and it's like, no, it's too long, and then you get the third attempt, and you're like, no, too formal, and make it funnier, and it makes it funnier, and so on, right? So the question is, how do we design the reward that would encourage the LLM to seek additional information, not seek too much of it, so that in the end it's effective in completing the task. So our approach has three steps. First is that we are going to generate these conversations synthetically. So we are going to use simulation to generate these conversations. The second thing will be that we are going to use kind of ideas from causal inference, from causal effect estimation, to really try to estimate what was the effect of the response of the LLM to the long-term outcome of the conversation. And by designing this reward function carefully, we'll then basically be using reinforcement learning-based fine-tuning of the LLM, so that it encourages it to actively seek for information, but also complete the task as quickly as possible, right? So in the end, what we want is, we want to complete the task quickly. We don't want to have a chat. We don't need to ask needless questions. We want to get to the final goal by actively and effectively asking clarifying questions, so that we can reach the goal quicker. So the key goal here is get to the end faster, not have a chit chat and keep asking the same thing over and over again, okay? So how do we do this? So the key is in this reward that we are using for reinforcement fine-tuning. And our reward has two parts. It has the extrinsic reward, which is how well did the conversation achieve the final goal. And then we have the intrinsic reward, which is how many tokens, how many iterations did it take. And then we basically use LLM as a judge to say, does this look like a good conversation, a happy conversation, or not? And then the way we formalize this is through this multi-turn aware reward, where basically what we want to do is we want to integrate over all, in some sense, all possible conversation paths. I try to write this here with that expectation. That kind of and that will allow us to estimate what is the causal effect of model's response. How does that influence the future trajectory of the conversation and the final reward of the conversation? And if you think about this, this sounds cool and nice, but there is a big problem with it, because it's basically assuming that you can kind of, you know all the possible paths the future will take, because now you can kind of sum over or take the expectation over all possible paths that the future will take. You can now say, okay, this is the effect on all possible futures of my current response. That's what we are trying to do here. We are trying to say, if I make this response, how will this affect all future conversations that will lead me to satisfying or completing this information task. So, and of course, getting these real-world conversations is very, very hard, and getting kind of all of them is impossible. So what we did here is we actually are using another kind of LLM agent to role play and kind of simulate user conversations. And the way this works is you give it the description, you say, okay, here is the task the user is trying to solve. You tell it about who the persona is, right? You know, you give it some instructions about the characteristics of the user. You give it the conversation up to the current turn, and then you ask it to generate the user's response. And this way, we can kind of take any partial conversation and we can keep evolving it forward multiple times, based on the, let's say, based on the response, right? And through this, we keep evolving it to the end, and then we see what was the quality of final task, how long did it take, and that essentially constitutes our reward. So the way we do this is basically, given the model's response, we forward simulate several different trajectories until they reach the goal. We then validate or try to understand each of these forward passes, both in terms of their accuracy, so have they achieved the goal, versus also their efficiency, how many iterations of the conversations did it take, and then we basically average rewards, and this is what is then used in this reinforcement learning-based fine-tuning of the LLM. So the idea here is, right, we have the user simulator that we have this multi-turn aware reward, and we use this signal then to actually fine-tune. So basically, we're doing training or fine-tuning of the LLM based on this multi-step reward. Okay. We've done a bunch of experiments. They are in the paper. The paper just got accepted tonight to ICML this year. But we also did a user study. So we recruited about 200 mechanical Turkers to ask them to complete a given writing task. And then we were asking them on a 10-point scale what their experience was. And we were measuring 3 outcomes: the quality of the generated document, what did the user think of the interaction, and also how long did it take them to complete the task. And we have 3. We have the base LLM, so this is just LLMs as they are today. We have what we call proactive base, which is an LLM, but with the instructions, with a prompt to ask clarifying questions and things like that. And then we have our Colab LLM that has been trained with this multi-turn aware reward to ask questions, but as few as possible to get to the task, to get to the completion of the task as quickly as possible. What do we find? We find that we are able to generate more accurate documents, that users prefer the interaction over the other 2 approaches, and actually we are able to save people about 10% of their time, right? So actually people are able to complete this task faster. What is maybe also interesting, if you look at the proactive base, so this is a LLM that's been instructed to be interactive and ask questions. It actually took people longer to complete the task, right? Because of basically kind of asking questions because of asking them, right? So here with this, we were kind of able to achieve these things. Also, just like to point out, maybe these differences, you think them small of a couple of percentage points, right? But maybe we should have asked people to be, we were not maybe too careful enough about how are we asking people to give us the scores. So we just said rank based on 1 to 10, and then everything is about if you ask Europeans, it would be 7. If you ask Americans, it's about 8 or whatever, right? I'm joking, but everything is good. So that's why I think the differences are kind of smaller than they should be. And then, of course, we asked also users for some feedback, right? And when they were using this base LLM to complete the task, they say, oh, AI just agreed with me on pretty much everything. There was no debate or discussion. Then for this prompt-based, ask clarifying questions type LLM, the feedback was, AI seemed to be very redundant, asking me the same questions over and over, and did not lead to good user experience, and also led to actually increasing the time to complete the task. But about the Colab LLM, they were saying, oh, it helped me really well to navigate what to say and what information is needed, really helped me focus on one part of the story at a time, asking questions and making you think of things you never thought about, and so on, right? So basically, with these questions, the LLM was seeking additional information that was actually relevant to complete the task quicker. So this was the third example of how could we use LLMs to more effectively search for information and navigate complex spaces. What is interesting that when we train the Colab LLM, it actually generalizes to new data sets and new tasks that it was never trained on. So here is a specific benchmark. It's called, it's basically an ambiguous type of question answering, where they have a set of ambiguous questions and a set of non-ambiguous questions. And the idea is that if the question is ambiguous, the LLM should ask clarifying questions. Whenever the question is non-ambiguous, the LLM should just provide the answer. If you look at what, let's say, GPT-4o is doing, whenever a question is ambiguous, it will only ask clarifying questions 15% of the time. And whenever it's non-ambiguous, it's just basically giving you the answer 95% of the time. When we look at Colab LLM, whenever the question is ambiguous, about half of the times, it's asking clarifying questions, which is what we want. And whenever the question is non-ambiguous, it still asks question, or it still gives immediately the answer, does not ask for additional questions 70% of the time, right? So this is good, right? Because whenever the questions are ambiguous, the Colab LLM kind of without knowing even that this benchmark is this way, is basically able to realize that we want to ask clarifying questions. And on the other side, whenever questions are non-ambiguous, maybe it's still asking a question sometimes, okay? So that also shows that this actually works even on benchmarks it has never seen, it hasn't been trained on. The last thing I want to mention today is about kind of pushing this idea of complex, kind of complex information seeking to the extreme. And the way you could push it to the extreme is to say, how about the most complex queries of all, right? And what are the most complex queries of all are scientific hypotheses, right? It's, I could say, mutations in this particular gene cause cystic fibrosis. This hypothesis up there, resulted in, I don't know, thousands of people's lives saved, resulted in a Nobel Prize, and so on and so forth. The last hypothesis about Alzheimer's disease, about accumulation of these peptides in the brain, has been out there for 30 years, and people are still trying to do something with it, right? So what I'm trying to say is that good hypotheses have tremendous consequences on our lives. And the question is, right, in the age of AI for science and so on, can we not only come up with hypotheses, right? Coming up with hypotheses is very cheap. LLMs are great at, coming up with hypotheses, but that's not the hard part. The hard part is to validate it and say, hey, is this actually true or not? And the question is, how could we automatically answer or validate these types of hypotheses as an example of almost like the most complex queries that we can think of. And if you think about this, this is really, really hard. It's a massive hypothesis space, right? We can make kind of hypotheses about everything. If you think about hypothesis testing, this is actually a very statistically rigorous task. You cannot just kind of hallucinate or ask the LLM, hey, what do you think, is this true? You really want to control the false positives. You really want to control the type 1 error. And you want to have rigorous statistical guarantees about the type 1 error. And then another interesting thing here that is different from the majority of the work that is trying to do this kind of hypothesis testing today, because those works are mostly doing kind of hypothesis testing in this kind of synthetic, toy-like, kind of mathematical environments, from 1 follows 2, from 2 follows 3, and then, infer something on top of it. What we would like here is something much more challenging, which is like, we would like to validate free-form hypotheses, right? Hypotheses that are just written in text, and we want to be able to validate them. So the question is, how do we rigorously validate this free-form hypothesis? And our key insight to be able to do this is basically that hypotheses cannot, or especially scientific hypotheses, they cannot be directly validated. Right? But what you can do is you can design falsification tests and try to falsify a hypothesis, right? So science is making constant progress by falsifying existing hypotheses and coming up with new ones, right? We never kind of know the absolute truth. We just know whether we can falsify the truth. And whatever we cannot disprove, then it must be true, right? That's kind of the mental model here, right? So if I say, a particular gene is a drug target for a particular disease, I cannot directly test this. But what I can do is I can test the implications of this hypothesis, right? I could say, if this gene is really linked to the disease, right? If it's a target for the disease, then it should be linked to the disease. So maybe the patients who have that particular disease, they should have an elevated expression of that gene or of the protein that is coded by that gene, right? So I could run a falsification experiment saying that the expression of this particular gene is not high in the patients with this disease, versus the alternative hypothesis being the expression of this gene is elevated in people with the disease. Okay, so what are we going to do is now we are basically going to give this global mother hypothesis to the LLM, and we are going to ask the LLM to come up with falsification tests, falsification experiments. And then we are going to have another LLM that is going to now execute these falsification experiments. And I could talk much more about what kind of environment we give to this LLM to be able to run these rigorous statistical tests and have all the bioinformatics tools and databases to be able to do that analysis over them. Happy to talk about that kind of offline. Okay? But the key idea of this paper is that basically, if you are doing these iterative falsification tests, each falsification test will essentially return you a p-value. It will return the outcome. But the problem is because these are iterative experiments, you cannot simply aggregate these p-values together into an aggregate p-value. You get highly biased results. So it doesn't really work. So what we've innovated in this paper is this concept of e-values, which are basically, you can think of them as p-values, but they have more robust statistical properties, right? I think if you want a p-value to be truly p-value, then the p-value distribution under the null should be uniform. For example, e-values do not have that requirement. Another thing that e-values allow you, they allow you to be aggregated together, even though the experiments are not independent. Right, so they can be sequential, right? So these falsification experiments, the next one depends on the outcome of the first one. So these experiments are not independent of each other, so you cannot kind of aggregate the p-values, but you can aggregate the e-values. And in the paper, we actually have a theorem that what we are doing and the properties that we require for what the agent, we call it Popper, is doing to be statistically valid are actually satisfied by the properties of the LLM. And I'm also happy to go in more detail and explain what do you need to satisfy in order for this to be true. But what kind of the key message here now is that we actually have now a system that is doing statistically rigorous hypothesis testing with statistically rigorous guarantees, which means we can control the amount of false positives or the type 1 error. So the way the agent works is that it has two components. On the input, it gets the big hypothesis, and it gets the type 1 error rate. It gets the alpha parameter. And then it has two components. The first component is the falsification experiment design agent that basically comes up with a null and the alternative hypothesis that is related to the big input mother hypothesis, basically designs the falsification test. And then we have a second agent who has access to the kind of the environment, to the tools, to the databases, to be able to then execute that test and come back with a test statistic, and then we transform that statistics into a e-value, and then we aggregate these e-values kind of iteration by iteration until we have sufficient evidence to either stop and say we cannot disprove this hypothesis, which means it must be true, or we actually go ahead and disprove it through this falsification tests. And just want to show you that kind of these things are really working quite impressively, right? So here I have a hypothesis that a particular gene regulates production of a particular protein, is kind of affecting a particular pathway. You can see 4 different falsification experiments on your left that the falsification experiment agent designed. And then each of these experiments, this falsification test, is then executed by another sub-agent who is actually now going and breaking that into a sequence of rigorous steps to be able to execute it. In order to be able to do this, the agent has access to, I think, 100 different biomedical databases and about 150 kind of bioinformatics type tools. And through that, it is basically able to autonomously now validate this hypothesis. We also did a user study where we recruited Stanford PhD students and postdocs, and we asked them to verify or try to falsify the same set of hypotheses. What we found out is that in terms of type 1 error estimation, actually humans were less precise. So the false positive rate of humans was about 22%, while Popper was at 10%, which was our target. And in terms of power, they were both at the same level. But what was interesting was that in terms of time spent, Popper was able to basically the AI agent was able to do the same work about 10 times faster. It wrote about almost 4 times as many lines of code and ran about 2.5 times more falsification tests, more statistical analysis to try to disprove hypotheses. What is interesting also, if you look at what kind of tests, what kind of analysis this was doing, it basically overlaps almost perfectly with the human, right? Here I show you this kind of Venn diagrams of tests that the AI agent Popper is doing versus the ones that our humans were doing, and you see basically a beautiful overlap. Popper is doing more tests, about 3 times more, so that's why there is more. There are additional things there on the left. But if you say, did human do something different than Popper? Each time maybe just 1 test. But both in terms of falsification experiment types, as well as in terms of what kind of statistical tests were used in this falsification experiment. So this is very interesting, right? Because now basically it allows us to essentially, or at least points us towards automatically validating hypotheses. And I think where this would be very, very useful is especially when you are doing, let's say, exploratory data analysis. Today, you have to do that by hand. But you could be using this type of agent to actually come up with this, let's say, pre-verified hypothesis or promising hypothesis, then you, as a human scientist, can go and actually further rigorously analyze, right? So a tool like this could be extremely useful. And we are now working with a bunch of labs in biology and School of Medicine at Stanford for them actually to adopt this and start using this in their daily lives. So this is what I prepared for you today, is really this idea, if I have this complex web, complex information system, how can I build kind of the next generation of tools that allow me to answer complex queries, mixed over structured, unstructured data, and kind of I took you on that journey. We first defined the Stark benchmark, which was to be able to measure progress in this complex question answering. Then I showed you Avatar, which was this contrastive reasoning-based idea of self-improving prompt generation, if you want to think of it that way, and really teach the LLM to use the tools more effectively. Then we talked about Colab LLM, which is about how do we need to actually train large language models to be interactive and to seek additional clarification questions. And basically that the claim is that the current way how we are training this system, they are not encouraged to ask clarifying questions, so they never do it. And then in the end, I showed you Popper, which was really the idea, okay, can we push this to answer the most complex queries of them all, which is validating scientific hypotheses. So, where is this taking us? Right? If you think about where this is taking us, it's really taking us towards this kind of complex compound AI systems that are composed of many different components that have access to many different tools. And they need to, all these things need to work in synchrony so that the end result is good, so that the task is completed. And if you think about this, these things get, or will get even more in the future, fragile, right? Any single kind of mistake in this kind of complex closed loop processes can have big downstream consequences, right? And becomes a really good question, how do we build this type of compound systems? How do we make them robust? And how do we make sure that they don't kind of fail in all kinds of ways, right? So what we are interested in is, how do we optimize these type of systems? How do we make them safe? How do we make them kind of fail-proof? How do we make sure that the error does not accumulate or some early mistake does not lead to very bad outcomes at the end, let's say, of the reasoning process. And of course, if you think about this, it opens a lot of open questions, right? It's a lot of open questions about integrity and reproducibility. If you think both kind of, as I was saying, around hypothesis testing and so on, but also about any kind of complex question answering. How do we make these things transparent, and how do we make them reproducible, right? LLMs have a temperature parameter. Everyone gets a different answer. But so how do I deal with that? It's also interesting to think about bias and representation, right? How useful will these agents really be, and whether they will be, let's say, biased towards popular or mainstream results, and because of this, maybe the answers get monotone, maybe my hypotheses become useless because they're just kind of popularity-based. And maybe the last thing I want to mention is, the importance of human and kind of how the final judgments and how the human should be part of this loop. So it has to be collaborative, right? So the stuff we were talking about, collaborative LLMs, I think it's very important because it keeps the human in control, keeps the human in the loop. So with this, I just, leave you with the final thought that, we are kind of moving to these AI systems that are not just answering questions, but are, kind of evolving into these active collaborators that allow us, humans, accomplish our complex tasks. With this, I'm done. I acknowledge a bunch of collaborators from Stanford, Amazon, and Microsoft. These are the 4 papers that I talked to you today about. They are very, very new. And just, thank you, and happy to take questions.
Thanks for the wonderful talk.
Can you stand up and wave?
Oh, yeah.
Oh, okay, great. Hi.
Yeah, thanks for the wonderful talk. So I really appreciate the idea about unifying the reasoning with structured knowledge and unstructured data. But you present basically is a compound system, compound AI system like you described, and it faced lots of challenge during each stage. So do you think about maybe there will be a unified model that can unify reasoning on the structured data and unstructured data, so that we don't need such a compound system to conduct the reasoning and handle the complex web system?
That's a very good question. Maybe the way the world is moving forward very quickly, right? Maybe the way you would do this is that you would actually fine tune what seems to be the technique that is emerging is basically RL fine-tune directly on the traces, right? So you would still have, in a sense, compound system, in a sense that you have the tools, you have all these capabilities, but maybe if you have a frozen LLM, then I think you have to do what we did, which is basically the prompt engineering, but at least ours was automatically self-improving. The other option is what I showed in the third part of the talk is that if you have access to the parameters of the LLM, is to basically use RL to train the model to accomplish the tasks. And that seems to be kind of the emerging paradigm for building any kind of complex agents, right? It's not to say, oh, we are going to change the architecture and things like that. That's too complicated, too expensive to retrain and to do anything realistic. So the idea is more that you want to fine-tune the LLM as a reasoning agent to be able to effectively use the tools to get to the goal.
Yeah, thanks for the answer.
Yeah, thank you for the question. Okay, great.
Yeah, thanks for the interesting talk. That I think one of the slides you have measured the power, right?
Yes.
I'm very interested to know how you measure the human's power.
Great. I can clarify what power is, right? So type 1 error is the false positive rate, right? So type 1 error means I give you a wrong hypothesis and you tell me it's true. Okay, so that's a type 1 error. Power is I give you a correct hypothesis, but you are able to disprove it. Okay, so that's the way to think of power. Is that how often when things are really true, you also conclude that they are really true. So it's like true positive rate, and the other one was false positive rate.
Okay, got it. Thank you.
Yeah, thank you. And there is still gap, right? So it's possible there is still room for improvement.
Thanks for the talk. In both your avatar and your collab LLM work, you have the agent and then another LLM that's performing some sort of critic or generating data that a human might in the system. And I was wondering, do you have any insight on the relative strength required for this other LLM versus the agent? Does it need to be better? Can it be weaker?
Good question. Maybe just, do you have a specific part of my talk? Because I have some general thoughts about this.
No, anything you have would be great.
Yeah, so just I think it is like the selection of the LLM of the LLM model for different tasks matters quite a bit, right? If you are doing any kind of retrieval, you wanna use this basically embedding LLMs that were not trained on the next token prediction, but were trained with kind of a masked language model, kind of BERT style. Those tend to give you much better embeddings. The other, for example, interesting thing is in these question answering and hypothesis generation questions, you really need a super powerful LLM to be able to go from the main hypothesis to the falsification test. And the reason for that is the following, is that falsification test has to be relevant to the mother hypothesis. Right? I could say, oh, does this gene, is causally related with this disease? And then the falsification experiment is the sky blue? Right? If the LLM says, okay, we'll test this mother hypothesis by checking whether the sky is blue, then I'll get an amazing p-value, but that p-value has nothing to do with my top hypothesis. And for example, in those kind of cases, this is one example, it was very important for us to use this kind of powerful reasoning-based models. So yeah, the choice depends on the task.
Thank you.
Yeah, thank you for the question. Yeah, hi.
Hey, thank you for the talk. My question is on the first part, which is on question answering over these different data sources. So our assumption while we try to answer questions over KG and text is we assume that like that question is going to be answered by one of the sources. So let's assume, I don't know from which source the answer could come. So what kind of approach can we follow, like given a question and without knowing the underlying data source, how can a model identify which part it should look into to answer that question?
Good question. So, I think our work was really motivated by, me searching for light bulbs on Amazon, right? There is many different types of light bulbs, and you need a specific one with a specific, size and so on. And this kind of general keyword search just didn't work well, right? So we really said, okay, how could you answer queries that have both some kind of relational component where you really want to match on color, you want to match on type, you want to match on size, versus some, I don't know, more soft type of characteristics, right? So the answers are always in the product database. But the way to identify the answer is that you have to kind of navigate these different information sources, right? And then based on the query, the goal of the LLM is to come up with a strategy, use the tools that combine those different information sources to give you the answer. And it's up to LLM to decide whether to use the, let's say, knowledge graph more, or to go more into the reviews and product descriptions and so on. So we did not constrain about where is that information. We just wanted to ask this type of queries that have these characteristics of, this kind of soft match, as well as have some kind of hard match. That's maybe another way to think of this work. Yeah, thanks for the question.
Okay, thanks for your talk. And in the last paper pop, you showed that the AI system could be as good as PhD level scientists in the way of performing tests and experiments. I wonder, and I think a lot of us wonder, if in the future can AI system help to raise assumptions, hypotheses, or even to raise a hypothesis itself, which is most meaningful for human or for the whole world. So that's the question. Thanks.
Good question. So you are saying, okay. So if I understand correctly, you are saying we can generate hypotheses, we can validate the hypothesis, but now we would like to rank them so that we know how, let's say, beneficial to the society they are. Does that sound like? I think that's a good question. There was a beautiful paper presented at iClear in Singapore by my colleagues at Stanford, Tatsu and Dee, about doing a case study about the power of LLMs to generate realistic hypotheses. And they did a big user study when I think they recruited 200 or 300 researchers for them to validate this human-generated as well as LLM-generated hypothesis. And the results were interesting, right? Actually, human hypothesis scored, if I remember correctly, scored a bit higher on the feasibility component, but then on the innovativeness, humans actually preferred the LLM's hypothesis versus what other humans generated. So I think it's a very interesting question about, on the hypothesis generation side, whether those hypotheses will be useful, how realistic they will be, and so on, right? But regardless, if we can validate them, it doesn't matter how bad they are. We can still filter them out with an approach like ours. Yeah, thanks for the question.
Hey, thanks, Siri, for the talk. Really great one. I have a question on the popper. So I think there you showed that it has either similar power, but generates more experiments and code. And in the examples also, I think popper was running more tests. So I'm wondering, like, what is the efficiency? Are those, because the humans in both cases like ran much less tests. So were the humans running more efficient tests, or is just like efficiency is like similar among the tests?
So the false positive rate of humans was about 2x the false positive rate of popper, right? So the type 1 error of humans, if I remember, was 0.22, and the one of popper was 0.1. But I would call that about the same. So the way I would conclude is, in terms of kind of statistical performance, it's about the same. But the interesting thing is that these tools, are just faster. They basically allow us to accomplish tasks faster. You also saw the breakdown in terms of tests. The LLM is running very much kind of human-like tests, right? So it wasn't that humans would be doing something different. LLM is doing everything that humans are, plus more, because it's doing so much more in shorter time.
Good, makes sense.
Thanks. Yeah, thank you. Thanks for the question.
Hey, Jure, great talk. So I'm wondering, what's your view for where personalized intelligence or personalization is headed toward in the future? And so on one side, I suppose could be one version of, okay, we just throw all the user data and user personalized tasks into a pre-training and post-trained model. And so that model has personalized listening capabilities. And the alternative way is we could, okay, throw all the user data, all the user history into long context window, and so it's part of the prompt, and so the model can handle personalization task. So what's your view on both of these versions, and what do you see?
Great question, right? Like, I think this question of personalization is very important, and when what I mean by personalization is really kind of knowing who the user is, their background, and kind of have that context, because only with that context, the LLM will be able to effectively be a collaborator or to be a helper, a co-pilot, whatever you want to call it, right? And I think it's still an open question how to do that well, right? A natural way is what you say is to basically throw that into a massive prompt, into a massive kind of context window, and hope that the LLM will be able to kind of synthesize, summarize this. I think we've seen that these long context window models don't really are not able to effectively use the long context window, or most kind of that most useful information is at the beginning, so they never learn to look very far in the past. So maybe the question is to train them in specific ways that would actually make the full use of the window. But it's a good question. It's a good question how to do that. I think it's a very important one, and we don't have good answers yet.
Yeah, over
here.
here.
Okay.
Thanks a lot for the talk. I was really interested in the tool usage, and especially the tool usage in Popper, because it seems like at first we are using these LLMs as a tool, but with Popper it almost seems like the human becomes the tool of the LLM. Like the LLM is generating these hypotheses and then is using the human to create new data. Do you think that that's going to be kind of the future, or do you think the human is still the most like the lead in this scenario?
Yeah, good question. So let me just clarify. Popper, what I showed, is fully autonomous, meaning there is no human in the loop here. So all those falsification tests are actually not executed by human, they are executed by the machine automatically, okay? As I mentioned, so the way we did this is that we created like an environment of, I think, around, yeah, as I said, around 150 tools and about 100 biomedical databases that the agent has access to run this statistical analysis. So basically, the agent is writing Python code on top of these 100 databases and 150, bioinformatics tools to analyze the data to try to run the falsification test. So that's what that is. One thing that is different, I think, is also interesting is that, in Popper, basically, it's able to use these quite advanced bioinformatics tools quite well, right? And then at the early part of the talk, when I was talking to you about Avatar, I basically had those specialized tools, and those specialized tools, kind of the agent is not able to use really well. Okay, so I think there is a big difference between tools that are kind of public and there is a lot of information about them on the web, and because the LLMs have been trained on all that information, they're able to effectively use those tools. As soon as you bring in kind of private tools that the LLM has not seen, has not been trained on, then it's much, much harder for LLM to use those tools, even though those tools might be kind of more primitive than those advanced ones. So I think that's maybe just clarification. In terms of human, I think it's interesting. Maybe the way I would see this is that as a way, when we were talking to our collaborators in statistics department at Stanford, it's really a way to kind of do, to come up with hypotheses that are good to be validated by human, right? That are not just, random hypotheses, but are almost like semi-validated hypotheses. I think that's the way to use these things, is that they are basically able to filter from huge number of hypotheses to the ones that are really promising, and then the human can focus on those. That's our view of how these tools could be used. Of course, you could say, okay, let's now completely close the loop. Let's have the robots do things. But I think we saw yesterday, and as well as I would say the common opinion is that doing this kind of robots to do wet lab experiments is super, super hard and super, super challenging. So it's unclear how close we are to that reality. Yeah, thanks for the question.
Thanks for your inspiring talk. I'm also working on the large language models. I'm often thinking the question about what AI system will be like in the next 5 or 10 years. So my question is that what are the most representative components of the AI systems in the future?
I mean, I think this kind of common common patterns, I would say, or common components are emerging, right? Like, and I think it's become clear, right? Because initially we thought we'll be fine-tuning these models a lot, that everyone will have their own and so on. But now maybe the paradigm is a bit different, right? Is that basically we have this reasoner, we need access to some private structured, unstructured data database. We need these agents to be able to take actions. So they need access to tools. They need to be able to use those tools. And I think the second component is that these systems are getting into this kind of compound stage where you don't have just one LLM, but you actually have a set of these agents talking to each other. So I think to me, those are the kind of the key components. Is the collaborative part, is the reasoning part, and then it's the part of being able to take actions, to use tools, as well as the part of being able to have access to the knowledge that is different than what the model has been trained and tuned on. So those to me would be those kind of key components of this architecture that is emerging in this space. Hope that made sense. Okay.
Thank you very much. So a very insightful talk, and it's great to see the multi-agent AI systems, how is it going to help us in the future. So at the same time, so this could be actually misused. I'm wondering if you can share some thoughts on how you envision ensuring ethics or safety of these kind of multi-agent complex systems.
I think that's a great question, and I think it's a very important one. I think the answer, maybe the answer is, to me, is twofold. I think, and it basically, in both cases, it basically requires the human to be in charge and the human to be in the loop. I think we achieve this with two ways. One, I think, is the aspect of training humans how to use these tools and understand them. And then I think the second aspect is for human to be in charge. What I think is also nice, in some sense, added benefit of these systems is that in some sense they're very interpretable, right? We see the traces, the reasoning traces that we can audit, and we can always talk to them to further explain why or what were they doing and how, right? So from that point of view, I think it's quite interesting also in terms of being able to audit, being able to have the trace and so on. Yeah, thanks for the question.
I have a quick question. In the collab LLM, isn't it a misnomer to call it human LLM collaboration because humans were simulated, right?
Good question. Good. So a great point. I would not agree. The reason I would say is the LLM was trained on synthetic data. That is true, right? But what I showed you is a validation with real biological humans. Okay. So I think I would not say that right. Like what is interesting, yeah, that to train the LLM, we were using synthetic data, which I think is a plus, right? It means that it's easy to generate these synthetic traces, much easier, much cheaper than to go to real human conversations. But when the humans were using it, we kind of accomplished our goal of having this LLM that can collaborate with the human. So I think it's a benefit. It's not a drawback. Yeah, thanks for the question.
Thank you, everyone. I can see still have someone want to raise a question, but due to the time constraint, we cannot take the question anymore. But you are feel free to talk to Professor Jure after this talk and directly talk to him in person. And thank you, and please join me to thank you for Professor Jure for his wonderful talk.
Yeah, thank you.